Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics. In today's lecture, the contents will be the electron and hole currents across the p-n junction, current under equilibrium condition, calculation of the potential across the p-n junction. You have p-type material, n-type material. You combine them in order to make what is called a p-n junction. In electronics, you know a p-n junction or p-n-p or n-p-n configurations. Now, we are looking at combining the p-type material that you have got here with the n-type material. In the earlier lectures, we have already seen that the excess carriers on this side, p-type means what? P refers to positive. You have got excess holes. How do you get excess holes? By adding trivalent impurities, you are having excess holes in a p-type semiconductor. On the other hand, in the n-type semiconductor, because you have added pentavalent impurities like phosphorus and others, you get a 5-valent system. The 5th electron becomes free, and so the majority carriers on n type will be electrons, right. You see electrons here, they are the majority carriers, and they have got holes here in the p type. Now, we have combined these two. I told you in the previous lectures, the excess carriers that you have got on the p type. What are the excess carriers? The holes. There will be the minority carriers, electrons, which are not shown for the sake of clarity. The excess carriers will go from the p type to n type. Why should they go? Because of diffusion. Whenever there is excess kind of carriers, or you can take the thermal diffusivity, heat flows from high temperature region to the low temperature region. Similarly, here when you have got excess holes on one side and excess electrons on the other side, because you have got you do not have holes here, the tendency of the holes will be to go towards the n type, and similarly electrons will go towards the p type semiconductors. So, there will be flow of carriers or diffusion of carriers, and I told you ultimately you come across an equilibrium condition, namely there will be a region across the p-n junction which will be free from free carriers, which is devoid of free carriers, and you will be having only ionic layers. These layers that you have got here, only ionic layers are there. The circles, they refer to the negative ions, again negative ions. On the other side, you have got positive ions, they are the ionic layers. Now, this region is called the depletion region. Why is it called depletion region? Because it is depleted of free carriers. You do not have electrons, right? You want free electrons here, you do not have free electrons here. The free holes that are available on this side, they are absent here. Therefore, this region, the presence of ionic layers are there, they are immobile, right? You have got ionic layers and the free carriers are not present in the depletion region. That is the reason why it is called depletion region, that is, it is a depleted of free carriers. Okay. So, you have got only ionic layers. Now, the region extends from x is equal to 0 to x is equal to x p, p refers to positive, right? You have got the p type. Then on the n type it extends up to x p plus x n. This is the width of the depletion region. Supposing a hole tries to go to this region, right, to the n type material, a hole from p type tries to go to the n type region, what will happen? When the hole comes here, it will be repelled by the ionic layers, right. So, there will be, it has to overcome a potential barrier, right, because the positive ions here will repel the hole. Similarly, when electron tries to go towards this region, suppose the electron is able to come up to this region, then it will be repelled by the negative ionic layers present here. So, either for the hole or for the electron from n type, both of them will come across a potential barrier when they come near the center of the p n junction. And in the whole of this lecture, we will be evaluating the potential barrier that the excess carriers have to overcome in order to go from one side to the other side. Generally, when you combine p and n, there will be the currents, the 4 components will be there. What is I 1? The whole current from p type to n type. P type, you know, contains the excess carriers are holes. The flow of holes from p type to n type, that makes I 1. I 2 is the electron current from n type to p type, that is the current I 1 and I 2 are the currents due to the flow of excess holes and excess electrons respectively, whereas the I 3 and I 4 are due to the minority carriers. Electron current from p type, in the p type the holes are majority, or the minority carriers, electrons are minority carriers. So, the electron current from p type to n type is I 3 and I 4 will be again the minority carrier current, that is due to the holes. So, I 4 will be the whole current from n type to p type. The condition in equilibrium in the p n junction not connected externally, when it is not biased, right. We are going to bias it finally, right, positive bias or negative bias. When in the unbiased state, when you do not apply any electric field or when you do not apply any potential, then the total current should be equal to 0, that is I 1 plus I 2 plus I 3 plus I 4 should be equal to 0. That is the current under equilibrium condition. The space charge layer at junction is called the depletion region, as you have seen, and I am mentioning here what is x p and x n. X p is the extent to which the ionic layers are present in the p type, and similarly in the n region the space charge layers give rise to a potential barrier, as I told you just now, which can be determined by solving Poisson's equations in one dimension for the 2 regions, because Poisson equation is nothing but a marriage between the potential and the charge density. You all know the Poisson's equation, del square V is 8 pi minus 8 pi rho of r. So, you are connecting the potential and the charge density, and so the potential barrier can be obtained by Poisson's equations, right. This is the potential profile across the p n junction. I mentioned about this is the p type, this is the n type, and if a carrier tries to come here, then it has to overcome a barrier of this kind. So, theta naught is the height of the potential barrier. You know, the electrostatic potential is a long range potential, right. Hole is here. If an hole tries to come to this region, it will experience the repulsion due to the positive ionic layers, right. It is a long range potential. Even if your hole is here, this hole will experience a long range repulsion coming from the positively charged ionic layers. So, that is the reason why it is graded, right. So, you have got a graded potential barrier. You have the potential profile, as I told you, will look like this. So, there is a graph drawn between the potential theta along the y axis and the distance along the x axis. That is, you have got the p type material here, the n type material here, this is the p n junction. So, the ionic layers are present from x equal to 0 to x p, and the other kind of ionic layers will be present from x p to up to x p plus x n, that is in the n type region, right. Okay. And if N A is the number of acceptor atoms per unit volume in the p type material, the charge density in the region from x equal to 0 to x equal to x p, the charge density means what? Charge multiplied by the number density. The N A is the number of acceptor atoms per unit volume. So, the charge density will be minus E times N A, because you are having a minus sign because of the fact that you have got negative ions, and so you have got minus E N A is the charge density, because the acceptors are all ionized in this region. So, you have got ionic layers, negatively charged ionic layers are present in that region. Similarly, if N D is the number of donor atoms per unit volume in n type material, the charge density in the region x p to x p plus x n is plus E into N D, because you have got positive ions. I will show you here, you have got positive ions on this side, and the charge density in this region will be given as E times N D, right. This is what you have, the charge density in the region. So, if theta 1 is the potential in the region x equal to 0 to x p, this is the region where the potential is assumed to be x 1, and theta 2 is the potential in the region x equal to x p to x p plus x n. Extension of this region x p to x p plus x n, the potential is taken to be as theta 2, whereas this potential here will be theta 1. The Poisson's equation for the two regions can be written down in terms of E into N A and E into N D. And let us now write down the Poisson equation. The Poisson's equation that is valid for the region x equal to 0 to x equal to p will be d square theta 1 by dx square. As I told you, theta 1 is the potential in that region. The d square theta 1 by dx square will be equal to minus rho by epsilon, and that will be equal to E into N A by epsilon, because the charge density will be E times N A. In the other case, it will be E times N D. In the region from x p plus to x p plus x n, the potential can be written as d square theta 2 by dx square, that is equal to again minus rho by epsilon, that will be equal to E into N D by epsilon. Now, you can write d theta 1 by dx as E N A into x by epsilon. That means you are integrating, right. You have got the d square theta 1, then upon integration d theta 1 by dx will be equal to E times N A into x by epsilon plus A, where A is the constant of integration. Now, we have to find out the constant of integration, or we have to eliminate it, right. Assuming the potential of the p type material to be 0, and considering the fact that the entire p type material on the left of x equal to 0 is neutral, and the left of x equal to 0 is neutral, means your d by dx of the derivative of the potential d theta 1 by dx will be 0 at x equal to 0. This theta 1 is the potential here. What I assume is, the potential here will be 0. The potential rises like this, right. The potential from x equal to 0 to any point less than x equal to 0 will be equal to 0. So, here again the derivative will be 0, right, the potential is 0, and so the derivative also should be equal to 0. So, I am talking about the point x equal to 0 for getting rid of the constant a. So, d by dx of d theta 1 by dx will be 0 at x equal to 0. Okay. D theta 1 by dx hence will be equal to E times n a into x by epsilon. Integrating the above, your theta 1 will be E into n a into x p square by 2. So, upon integration your x will become x square by 2, that is what I am having here, x square by 2 into epsilon plus again plus b, another constant of integration. You get rid of b again, if one takes theta 1 is equal to 0 at x equal to 0, it leads to b equal to 0. If one takes theta 1 is equal to 0 at the point x equal to 0, that is the origin of the depleted region, it leads to the constant b become equal to 0, thereby your theta 1 becomes E times n a into x square by 2 epsilon. That is the expression for theta 1. A similar expression we have to obtain for theta 2 also, that is the second region. So, employing Poisson's equation from x equal to 0 to x p, d square theta 1 by dx square is equal to minus rho by epsilon, that will be equal to E times n a by epsilon, that is what we wrote earlier, right. Now, coming back to the other region, this is the region starting from x equal to 0 to x p. Now, we have to concentrate in the other region of the depletion region extending from x p to x p plus x n. In this region, as I told you, the potential will be theta 2. Now, we have to connect the charge density and the potential. Theta 2 is the potential, the charge density will be n d, the donor atoms, right. You have got donor ionic layers due to the after donating the electron there will be positive ions, and so the charge times the number density of positive ions you have here, that gives rise to a charge rho. That so, in this region d square theta 2 by dx square will be minus rho by epsilon, that rho will be what? Rho is the charge density will be due to ionic layers. How many atoms are there or how many ions are there? N d is the number of ions. Each ion will give a charge E or will possess a charge E, therefore, be E times n d by epsilon. So, you write now d theta 1 by dx will be E times n a into x by epsilon plus a, where a is the constant of integration, and the above relation shows that in the region from x p to x p plus x n, d square theta 2 by dx will be minus E n d into x by epsilon plus c, where c is the constant of integration. The electric field must be continuous in the space charge regions, right. In the space charge region, the potential profile I showed, it will be continuous. So, whatever I am writing here, d theta 1 by dx at x p is what? That is the central line, that is the dividing the within the depletion region. You have you start from 0 to x p, then you go from x p to x p plus x n. So, at the point x p, the potential is smooth, that is what you have seen already. So, the potential profile I showed you. So, this I am referring to x p. So, the potential should be continuous. Therefore, what I say is when I call the potential as theta 1 here, the potential here is theta 2, you are the derivative of the potential at this point, the derivative of the potential at this point, both of them should be matching, because it should be for a continuity condition. The electric field must be continuous in the space charge regions. Hence, d theta 1 by dx should be equal to d theta 2 by dx at x equal to x p. So, that makes your E times n a by x p by epsilon to be equal to minus E times nd into xp by epsilon plus c. This expression c will become E into xp by epsilon multiplied by Na plus Nd. Okay. You have got Na here, Nd here. So, your C is found to be having this value. Okay. Now, d theta 2 by dx will be can be rewritten as minus E into Nd into x by epsilon plus E into xp by epsilon into Na plus Nd. Na is the number of acceptor atoms, Nd is the number of donor atoms. Now, theta 2, what is theta 2? That is a potential in this region, right. Theta 2 will turn out to be minus E into Nd into x square by 2 epsilon plus E into xp by epsilon into Na plus Nd multiplied by x plus d, where d is the constant of integration. The potential theta 2 at x equal to xp must be the same as theta 1 at x equal to xp, and the potential should be continuous at xp. So, theta 2 at x equal to xp will become minus E n d xp square, because I am referring to the point xp, right. So, xp square by 2 epsilon, here you got plus E into xp square by epsilon into Na plus Nd plus d. Okay. This is what you have at as theta 2. The theta 1 that I had earlier at x equal to xp will become E into Na into xp square by 2 epsilon, that will be equal to theta 2 at x equal to xp. So, you will have an expression of this kind, E minus E times Nd into xp square by 2 epsilon plus E into xp square by epsilon into Na plus Nd will be d. From this you can evaluate your d. Your d will be the constant of integration, d will be E minus E times xp square by 2 epsilon into Na plus Nd. So, this is the potential profile that I am repeatedly showing to make you to understand what is the potential here, what is the potential here, and how we are evaluating theta 1 and theta 2, how we are evaluating the constants of integrations, that is your a, b, c and d, yet another constant of integration. And now comes the potential theta 2 at any point in the region x equal to sp to xp plus xn may now be obtained by substituting for d in the equation for theta 2. You have got the expression for d, that value of d should be substituted here and to obtain theta d. That is what I am doing here. You see, after substitution for d, you have an expression of this kind, where you find the potential theta 2 as a function of x will be equal to minus E times Nd to x square by 2 epsilon plus E into xp by epsilon into Na plus Nd into x minus E into xp square by 2 epsilon into Na plus Nd. And the potential with its reference 0 potential at x equal to 0 is called the contact potential. It is called the contact potential. So, your theta naught, what is theta naught? The height of the potential that you have got, right. This is theta naught. This is called the contact potential. So, this contact potential is to be evaluated. This can be shown theta naught having an expression value of this kind, and we will go to the summary part. The total current in equilibrium condition should be 0. The potential profile is calculated using Poisson's equation. Poisson's equation plays a very important role in evaluating what is called the contact potential, and again the the potential profile, the value of theta 1, theta 2, wherever when we want to evaluate the potential theta 1, theta 2, we make use of the Poisson's equation, because it connects the charge density and the potential. The questions are: how are space charge layers formed? Number 2, what is Poisson's equation? How do you evaluate theta 1 and theta 2? With this we come to the end of the lecture number 12. The rest of the things, namely the contact potential, the expression of the contact potential, and ultimately the junction diode equation or the rectifier equation. You know, the p-n junction can be used as a rectifier. These things we will see in the next lecture. Thank you.